Hansen, a renowned climatologist. His recent paper, Another El Nino Already, What Can We Learn From It?, suggests some truly concerning global temperature projections. Rachel, what's Dr. Hansen's primary warning for us?
Well, Jake, Dr. Hansen is sounding the alarm that another El Nino is likely just 3 years after the last one. Normally, such a quick return might indicate a moderately strong event at most. However, the paper predicts that even a moderately strong El Nino could lead to record global temperatures in 2026 and potentially even higher temperatures in 2027. He attributes this extreme warming not so much to the El Nino itself, but primarily to high climate sensitivity and a recent rise in net global climate forcing.
So it's not just the immediate weather pattern, but a deeper, more fundamental shift. Hansen also points to an acceleration of global warming that began around 2015. What does this acceleration imply for how quickly we might reach critical temperature thresholds?
This acceleration is significant. The report suggests that a 2 degrees C rise in global warming is now more probable in the 2030s, rather than the middle of the century as previously thought. For policymakers, understanding these current temperature changes as quickly as possible is critical. Dr. Hansen emphasizes this urgent timeline.
Before we dive deeper into those implications, can you clarify how these global temperature changes are measured and tracked? The paper mentions both 12-month running means and annual means.
Certainly. The blue curve in Figure 1 of Dr. Hansen's paper, for example, represents the global temperature anomaly's 12-month running mean relative to the 1880-1920 base period. This is the earliest period with enough data for a reliable global mean. The black squares on that curve show the annual mean. While researchers often display annual temperatures connected by straight lines, as seen in Figure 2, Dr. Hansen prefers the 12-month running mean. He argues it removes noise and seasonality, offering higher temporal resolution. This means we don't have to wait until December for annual data, and it's more informative for short-lived climate effects like volcanic eruptions, which can happen in any month.
That makes sense for getting a clearer, real-time picture. Now, the El Niño-La Niña cycle is the primary cause of global temperature oscillation. How does this cycle actually work at a fundamental level, and why is it so challenging to predict?
During the more persistent La Niña phase, easterly trade winds in the equatorial Pacific push warm surface water toward the western Pacific, causing cold, deep water upwelling near South America. This ocean temperature pattern creates an atmospheric circulation that strengthens the trade winds and maintains the temperature pattern. If westerly wind bursts are strong enough to move warm water eastward, this reinforcement, known as Bjerknes feedback, can momentarily reverse and trigger an El Niño. However, forecasting the occurrence and magnitude of El Niños is difficult due to several factors. These include the initial ocean state, the phase of natural atmospheric disturbances like the Madden-Julian oscillation, erratic wind bursts, and even salinity anomalies in surface waters.
So there's a complex interplay of forces. Hansen suggests that the peak of this upcoming El Niño and the subsequent La Niña valley could offer crucial data. What exactly could they help confirm?
They could help confirm the reality of this acceleration in global warming and determine whether the average global temperature has already reached 1.5 degrees Celsius, something Dr. Hansen noted 2 years ago when many questioned the acceleration. He predicts that by the second quarter of 2026, the temperature will have risen by at least 1.4 degrees Celsius. This, in turn, supports the mechanisms he proposes are responsible for the acceleration: high climate sensitivity, at least 4 degrees Celsius for doubled CO2, and a reduction of aerosol cooling due to declining emissions from East Asia and ships at sea. He points out that a minimum of roughly 1.4 degrees Celsius would be strong support for global temperature acceleration, especially if this La Niña minimum is higher than any El Niño maximum in the previous decade, even a super El Niño.
That's a direct challenge to the Intergovernmental Panel on Climate Change's assessments, isn't it? Hansen explicitly states that the IPCC's global climate model-dominated process results in a lower best estimate of climate sensitivity, around 3 degrees Celsius for doubled CO2, and a limited contribution from aerosols. How does his analysis differ?
It's a stark contrast. Dr. Hansen argues that the IPCC's over-reliance on GCM temperature simulations over the last century led to an underestimation of climate sensitivity. GCMs struggle more with modeling cloud changes, which are a major climate feedback, compared to water vapor feedback. This typically results in models showing a climate sensitivity of around 3 degrees Celsius for doubled CO2. In contrast, Hansen's work, based on 4 independent evaluations, finds climate sensitivity to be at least 4 degrees Celsius for doubled CO2. He also suggests that if aerosol cooling increased moderately between 1970 and 2005, as aerosol cloud modeling indicates, then this higher sensitivity is consistent with the observed global warming of 0.18 degrees Celsius per decade after 1970.
So, the role of aerosols and how models account for them seems central to this discrepancy. But what about the El Nino itself? The paper talks about how human-caused global warming might affect how we interpret the natural state of the El Nino-La Nina cycle.
That's a really important nuance. Dr. Hansen cautions that because global warming affects sea surface temperatures everywhere, the traditional Nino 3.4 SST, which defines El Nino status, is no longer purely natural. Global warming can decrease La Nina depth and exaggerate the strength of recent El Ninos. For instance, the 2015-16 El Nino might appear stronger than the 1997-98 El Nino of the century when looking at Nino 3.4 SST in Fig 3, but its anomaly was actually less significant relative to surrounding ocean temperatures. To address this, NOAA introduced a Relative Oceanic Nino Index, or RONI Nino 3.4, which subtracts the global tropics SST anomaly. RONI Nino 3.4 intensifies recent La Ninas and lessens the strength of the projected 2023-24 El Nino, likely providing a more accurate indicator, though it doesn't fully account for complex human influences on the cycle.
That's a crucial refinement for understanding the actual dynamics. Despite these advanced indices, forecasts for El Nino still seem to have a lot of uncertainty. Why is that?
There are several reasons. Even with model averages predicting an El Nino by June 2026, individual model runs show a wide range, and some don't even generate an El Nino. Forecasters are hesitant to make early predictions. Also, the short time since the last El Nino gives reason for caution. The paper points out that in the last 75 years, there isn't an example of a strong El Nino occurring just 3 years apart, possibly due to the time it takes for the ocean to restore lost heat.
Given that uncertainty, are there any other indicators that might offer a clearer or earlier signal?
Yes, Dr. Hansen suggests looking at the temperature anomaly in the equatorial upper ocean, specifically the top 300 meters, at longitudes 180 to 100 degrees W, as seen in Figure 5. He believes this upper ocean heat anomaly is a better predictor because 300 meters of ocean are less contaminated by human-caused warming. It also offers a longer lead time. The 12-month running mean of tropical Pacific upper ocean heat has a correlation of over 50% with global temperature 9 months in advance, compared to Nino 3.4's 4-month lead time. While Nino 3.4 was still in La Nina conditions at the end of December, the upper ocean heat anomaly had risen to 0. If this index continues to rise, it suggests an El Nino could peak near the end of 2026.
So even with the inherent uncertainties, Hansen makes a calculated projection for global temperatures. What does his educated speculation suggest about the coming years?
He estimates that after reaching a minimum of roughly plus 1.4 degrees Celsius in the first half of 2026, global temperature could rise to approximately plus 1.7 degrees Celsius in the first half of 2027, driven by even a moderately strong El Nino. This projection, he argues, could force a reckoning of fundamental climate physics issues, reinforcing his conclusions that climate sensitivity is much higher than the IPCC's best estimate, and that global warming has accelerated over the last decade due to an increased growth rate of net climate forcing, largely from a decrease in human-made aerosol emissions.
That really brings us back to the core debate about climate sensitivity and the role of aerosols. You mentioned the IPCC's GCMs struggle with cloud feedback. Can you elaborate on that?
The GCMs, or global climate models, have difficulty modeling cloud change, which is a significant climate feedback. This often leads them to produce a conservative climate sensitivity of around 3 degrees for doubled CO2. Because of this, these GCMs can predict observed warming during the period of rapid, linear global warming from 1970 to 2010 without necessarily accounting for changing aerosols. However, Hansen's analysis suggests that aerosol cooling likely increases increased during that time at least until around 2005 due to the nonlinear aerosol effect on clouds. More emissions into an already polluted atmosphere have less impact than emissions into a cleaner one. His modeling, which considers geographic distribution of emissions, estimates aerosol cooling increased between 1970 and 2005, with a change in aerosol forcing of roughly negative 0.5 watts per meter squared. To match the observed post-1970 warming with this aerosol forcing, a climate sensitivity of at least 4 degrees for doubled CO2 is required.
So, a crucial discrepancy rooted in how aerosols and clouds are modeled. What about the turning point Dr. Hansen identifies for this significant change as likely being somewhere between 2010 and 2015?
Dr. Hansen pinpoints a single turning point for this significant change as likely being somewhere between 2010 and 2015. Figure 10 illustrates quantities pertinent to main forcings like greenhouse gases and aerosols. Greenhouse forcing increased by roughly 20% between 2010 and 2015, with the largest increase closer to 2015. Simultaneously, satellite data in Figure 10 shows that China's sulfate emissions decreased most quickly between 2013 and 2014, and ship emissions saw their biggest drop in 2020. This change in Earth's absorption of solar radiation, largely due to decreasing aerosols and feedback mechanisms like reduced cloud albedo, changed significantly around 2015. This period marks where global warming really started to deviate from its previous linear trend.
That helps clarify the underlying physical changes driving this acceleration. Finally, Hansen talks about why the next year or two will be particularly informative for understanding climate sensitivity and global warming acceleration. What makes this period so crucial?
Climate feedbacks like changes in clouds or ice don't kick in immediately after a climate forcing is applied. They become active only gradually in response to the delayed temperature change. So a short-lived event, like an El Niño or a volcanic eruption, doesn't by itself tell us much about long-term climate sensitivity. However, after a few years, the responses for different climate sensitivities start to diverge significantly. A long-term forcing produces a growing response. And after a few years, high climate sensitivity leads to a much greater climate response than low climate sensitivity. The accelerated warming we're seeing, especially if amplified by a significant El Niño, will make it increasingly difficult for the IPCC's models, particularly those with low climate sensitivity, to ignore these discrepancies.
Dr. Hansen's paper, Another El Niño Already, What Can We Learn From It?, lays out a compelling argument for a reassessment of our understanding of global warming's pace and severity. Rachel, it seems the key takeaway is that we need to realistically understand the situation to effectively address it.
Precisely, Jake. Dr. Hansen emphasizes that increased public awareness and policy development are essential. He suggests that the current complacency, or the idea that 1.5 degrees Celsius isn't so bad, we can deal with 3 degrees C, will vanish as the effects of climate change intensify and global temperature approaches plus 2 degrees Celsius. He believes advances in climate science over the next 5 to 10 years will be vital as pressure for policy action increases.
A powerful message on the urgency of our climate situation. If this discussion resonated with you, consider sharing it with someone who might find it valuable.
Climate sensitivity is a very important measure in climate science. It tells us how much the Earth's surface will warm if the amount of carbon dioxide in the air doubles. The formal definition is the change in the surface temperature that happens when the amount of carbon dioxide in the air or other radiative forcing changes. 2,223. This idea helps scientists figure out how bad climate change is and how far it goes. The Earth's surface gets warmer because there is more CO2 in the air and more nitrous oxide and methane, which are other greenhouse gases. The rising temperatures have other effects on the climate system. Climate feedbacks are the effects that happen as a result of these changes. Self-reinforcing feedbacks include things like ice melting that reflects sunlight and higher evapotranspiration. The second effect raises the amount of water vapor in the air, which is a greenhouse gas in and of itself. Scientists are not sure how strong these climate feedbacks are. Because of this, it's hard to guess exactly how much warming will happen if greenhouse gas levels go up. If scientists are right and climate sensitivity is on the high side, it will be even harder to reach the Paris Agreement goal of keeping global warming below 2 degrees Celsius. The transient climate response is the first rise in global temperature when CO2 levels double. The equilibrium climate sensitivity is the bigger long-term rise in temperature after the planet adjusts to the doubling. There are a few ways to estimate climate sensitivity by looking directly at temperature and greenhouse gas levels since the Industrial Revolution started in the 1750s, by using indirect measurements from the distant past of the Earth and by simulating the climate. Jake. So it's not just the immediate weather pattern, but a deeper, more fundamental shift. Hansen also points to an acceleration of global warming that began around 2015. What does